You've heard people say, we can get to Mars, but nobody really tells you how fast can we actually do it? Are we stuck with slow year-long cruises through radiation? Or is there a way to punch a hole in that timeline and turn Mars into something that feels close? In this video, you and I are going to climb through every serious option we have, from today's rockets to nuclear, plasma and beyond, and by the end, you'll know which idea is winning the race to become the true fastest way to Mars. Start with a simple question: how far is Mars really? The average distance between Earth and Mars is around 140 million miles. That is the middle value. When the orbits line up well, Mars can come as close as about 35 million miles. When they line up badly, the distance can stretch to about 250 million miles. You're not dealing with a fixed gap, you're dealing with a moving distance that keeps changing as both planets orbit the Sun, non-stop year after year. Here is the direct problem. Earth and Mars are both moving very fast around the Sun. Earth moves at about 67,000 miles per hour, Mars moves at about 54,000 miles per hour. You're not targeting something that sits and waits for you. You are trying to match motion with another world that is constantly changing its position. If you launch at the wrong time, even if your rocket works perfectly and hits its planned path, Mars will not be where you need it to be when you arrive. So you might think, fine, just point the rocket at where Mars will be in the future and go in a straight line. How hard can that be? This is where orbital mechanics cuts in. In space, your ship is always under the pull of the Sun's gravity, so your path is a curve, not a straight shot. To reach Mars efficiently, you have to enter a specific curved path, an ellipse, that starts near Earth's orbit and stretches out to intersect Mars's orbit. The shape of that curve and the time you leave Earth have to line up with the future position of Mars with very high precision. That is why you cannot just aim and floor it. If you launch a few weeks early or a few weeks late, you still follow some version of that curved path, but by the time you get to where Mars's orbit crosses your path, Mars itself has already moved on. Instead of meeting the planet, you arrive at empty space, maybe millions of miles from your target, with no practical way to fix it. You do not get a second shot, and you do not have the fuel to stop, turn and chase Mars again. Missing the timing window is not a small error, it is mission failure. That timing constraint is what people mean when they talk about launch windows for Mars. Roughly every 26 months, the geometry between Earth's orbit and Mars's orbit lines up in a way that gives you a relatively efficient path. During that period, you can launch a mission that uses a realistic amount of fuel and reaches Mars in a reasonable time. Outside that window, you face a choice: accept a much longer trip with a strange trajectory, or pay a huge energy cost to try to force a faster path. So even before you talk about cutting travel time, you're locked into this schedule the solar system hands you, whether you like it or not. Now, what do we actually do with today's technology? What does a normal Mars trip look like right now? With standard chemical rockets using something close to a Hohmann transfer orbit, trips to Mars usually take about 6 to 9 months one way. That is the current baseline. You do a strong burn to leave Earth, you coast through space for most of the distance, then you burn again to slow down near Mars and either enter orbit or set up for entry into the atmosphere. It is not fast, but it is fuel efficient enough that we can actually launch these missions with present-day rockets and budgets. So when you hear people talk about fast missions to Mars, what they're really asking is can we beat that 6 to 9 month range without creating a mission that is too risky or too expensive to fly? Can we cut the trip to 4 or 5 months, or maybe even around 3 months, and still keep humans alive, protected, and able to land? Fast to Mars is not just about shaving time off the clock, it is about beating that baseline without breaking the whole mission design. Have we already done better with uncrewed missions? Have we actually proven faster trips are possible? Yes, but with important limits. Some Mars missions have used higher energy trajectories and cut the travel time down to something like 128 to 155 days, around 4 to 5 months. These are faster paths that burn more energy up front, trading extra fuel for earlier arrival. On paper, that looks close to what you would want for a fast human mission. But here is the catch. Those fast paths were designed for robotic spacecraft, with much smaller mass and no people on board. Many of them only had to fly by Mars or perform a simpler orbit insertion with hardware that could handle higher stresses. If you try to arrive at Mars that fast with a large crewed ship, you show up with a very high speed relative to the planet. That means extreme heating if you touch the atmosphere, intense loads on heat shields and structure, and a much more demanding capture burn if you try to slow down with engines instead. The faster you come in, the harder it is to avoid destroying the vehicle in those last minutes. That is why any honest plan for fast to Mars has to talk about arrival speed, not just cruise time. Cutting 2 months off the trip does not help you if the ship burns up or breaks apart in the final phase. For human missions, reaching Mars is only half the job. The other half is slowing down to a safe orbit or a safe entry speed. And that restriction limits how aggressive you can be with your outbound trajectory. Now put all of this next to the real speed ceiling in the universe, the speed of light. When Earth and Mars are at their closest, light takes only about 4 minutes to travel between them. When they are far apart, that signal time stretches to roughly 21 minutes. Every command we send to a rover on Mars, every image that comes back rides on those radio waves, crossing tens of millions of miles in a few minutes. That is what fast really looks like on a universal scale. Your ship sits far below that. Even on a high-energy, 4 or 5 month trajectory, you're crawling compared to light. The difference between minutes for photons and months for rockets is not just trivia, it is the main gap every advanced propulsion idea is trying to narrow. Nuclear thermal rockets, ion drives, plasma engines, and far future concepts like fusion or antimatter propulsion all point at the same problem. How do you move a heavy, fragile human habitat through that distance in something closer to weeks or a few months without crossing the line where the conditions become lethal? So here is the key question that sets up everything coming next. If plane distance, strict timing, and safe arrival already make fast to Mars this difficult, what exactly does the slow standard option look like? And why is it still the main method that we depend on? To see how extreme the fast ideas really are, you first need to understand the basic transfer orbit we use today. The quiet, efficient baseline that every new technology is trying to beat. What if the standard way to Mars is already using almost the least energy nature will allow, and that's still painfully slow? Before you talk about nuclear rockets or plasma drives, you have to look at the boring, brutally logical path we already use, because this is the thing every fast rider has to beat. First, you need to know what this orbit actually is. A Hohmann transfer is the classic minimum energy route between two circular orbits around the same central body, in this case the Sun. You start in Earth's orbit, you do one engine burn to stretch your path into a long oval, an ellipse, that just touches Mars's orbit on the other side of the Sun. Then you coast most of the way, and at the far end, you burn again to match Mars's speed. For Earth to Mars, that kind of trajectory usually means something like 8 to 9 months, door to door. In rocket terms, it is very good. You spend as little energy as possible to move from one orbit to the other. In human terms, sitting in a metal can for most of a year, getting slowly cooked by radiation, it is not good at all. So if this orbit is so slow, why do engineers still respect it so much? Because it shows you the floor on energy. You cannot do much better on fuel use than a Hohmann transfer without changing the basic rules of the game. If you want to arrive sooner, you must pay more somewhere, more fuel, more engine power, more heating at arrival, more risk. That is why the Hohmann path is the most efficient, not the fastest. It is like the slow lane on the highway that gives you great gas mileage, but makes you late for everything. Now, how do you actually measure the price of changing orbits like this? How do you keep certain score? This is where delta V comes in, and you really cannot ignore it. Delta V just means change in speed. It is the total amount of velocity you need to add or remove during a mission. For an Earth to Mars Hohmann transfer, the delta V you need is several miles per second when you add up leaving Earth's orbit, adjusting in deep space, and then matching speeds near Mars. Think of it like a speed budget. Your rocket only has so much fuel, and that fuel can only buy you so much total change in speed. Here is the key point. If you spend more of that speed budget at departure, By burning harder and longer, you leave Earth faster and your transfer orbit cuts inside the usual path so you reach Mars sooner. If you also spend more at arrival, you can slam on the brakes harder and safely capture into orbit even though you showed up going faster. That sounds great, until you look at the trade. More delta V means more propellant. More propellant means heavier vehicles. Heavier vehicles mean you need even more propellant just to move all that extra mass. You get into a loop where every extra bit of speed costs you more than the last one. So if this is that expensive, why are we still okay with 6 to 9 months for most missions? Why not push harder by default? Because robots do not care about long trips the way humans do. If you are sending a 1-ton rover, like Curiosity or Perseverance or a lander or an orbiter with no crew, a 7-month cruise is not a problem. You do not worry about bone loss, mental health, or lifetime cancer risk for a machine. That is why most Mars missions so far, from Viking in the 1970s to Mars 2020 with Perseverance, have used some flavour of this minimum energy transfer. It lets you put more mass into the payload and less mass into extra propellant to shave a few weeks off the timeline. Take Perseverance as a concrete example. Mars 2020 launched in July 2020 and landed in February 2021, about 7 months of travel. The total path it took around the Sun was not the straight line distance between Earth and Mars, it was a long arc of around 300 million miles, because both planets were moving the whole time, and the spacecraft was following that stretched ellipse. Relative to the Sun, Perseverance cruised at speeds on the order of about 24,600 miles per hour. That sounds fast, and it is fast, but because the distance is so huge and the path is curved, it still takes months. For a robot, that's fine. For humans, it starts to look like a medical problem. And that's where the hidden time bomb shows up: radiation. During a Hohmann-style cruise, your ship spends 6 to 9 months outside Earth's protective magnetic field, in deep space, where cosmic rays and solar particle events are a constant threat. Cosmic rays are high-energy particles coming from outside the solar system. Solar storms throw bursts of protons and other particles at high speed. Both can pass through your ship and your body, damaging cells and DNA. Over months, the dose adds up. Space agencies set career radiation limits for astronauts, a maximum dose they should not exceed over their entire career. A 9-month trip to Mars and then another 9 months back, plus time on the surface, pushes you close to those limits. So when people say faster to Mars is safer, it is not just a slogan. Every month you cut from the cruise is a month less of radiation. It is less chance that a big solar storm hits you while you are far from any shelter. It is less time for small errors, leaks or hardware problems to build up. The longer you are in transit, the more chances something goes wrong. The Hohmann transfer is great for saving fuel, but for human health it is expensive. Time in deep space is a kind of slow damage. Put all of that together and you get the benchmark you actually have to beat. Right now, the standard looks like this, roughly 6 to 9 months of travel time, total delta in the single-digit miles per second range, and rockets that are only chemical, burning liquid propellants with engine technology we already know how to build and fly. Any future system that claims to be fast to Mars has to bend that basic trade. It has to either spend more energy, use a more efficient engine so each pound of propellant buys more speed, or use smart tricks with gravity and atmospheres so you get more for the same fuel. The question is, how far can you really push today's rockets before you hit a wall where more speed stops making sense? If you keep chemical propulsion and you just push it harder with refueling and clever trajectories, how much can you shrink that 6 to 9 month window before the cost and risk explode? What if I told you that with the rockets we already have, no nuclear, no fusion, you could cut the Mars trip almost in half, but only by pushing everything to the edge? You do not need a sci-fi drive to go faster. You can just lean hard on the physics of chemical rockets and see how close they can get to their breaking point. Start with the simplest move. You take that normal Hohmann transfer you just learned about, and you basically hit it harder at the start. Instead of doing the minimum burn that gives you that long, slow 8 to 9 month ellipse, you add extra delta at departure. You leave Earth faster, you bend your trajectory into a higher energy arc. That higher energy path crosses Mars's orbit sooner, so your trip time drops. You can design fast transfer trajectories where a mission that would have taken, say, 8.5 months gets pushed down closer to 6 months, using nothing more exotic than the engines we already fly. But every bit of that speed comes with a bill. To add that extra delta V at the start, you need more propellant in your departure stage. Your rocket has to carry more fuel off the launch pad, or you have to send fuel up separately and transfer it in space. And when you arrive at Mars at the end of this fast transfer, you are moving faster relative to the planet than you would on a Hohmann orbit, so now your arrival burn, or your heat shield, has to handle a much tougher job. You did not just make the cruise shorter, you made the front and back ends of the mission more violent. So how far can you push that idea with a real vehicle, not a thought experiment? This is where SpaceX's Starship enters the picture and shocks people. Starship is a fully reusable methane and oxygen rocket system, meant to take more than 100 tons to low Earth orbit when refueled. Recent trajectory studies suggest that if you take a Starship, fill it completely in orbit, and fly a very high energy path to Mars, you could get humans there in something like 90 to 104 days, roughly 3 to 3.5 months. That is still chemical propulsion, no reactor, no ion drive, just a very large, very capable rocket pushed to aggressive trajectories. On paper, that means you go from the usual 6 to 9 month range down to around 3 months, with tech that is basically off the shelf once Starship is fully operational. The catch is that everything has to line up. You need the right launch window, you need the ship fully fueled, you need the structure and the heat shield size for the harsher arrival, and you need mission control to be comfortable with much less margin for error. It is like turning a calm cruise into a sprint. The distance is the same, but everything about how you ride it feels different. The key enabler here is something you do not see on old Apollo-style missions, in-orbit refueling. On a normal rocket launch, everything you need is stacked on top of one booster, you go up once, and you are done. With Starship-style architectures, you can do something else. You can launch an empty or partially fueled Mars ship to Earth orbit first, then send up multiple tanker starships, each full of propellant, and transfer that fuel in space. After several tanker flights, your Mars ship ends up in orbit with its tanks completely full, ready to do big burns that would have been impossible if it had to lift all that fuel straight off the pad in one shot. This is why Elon Musk has talked about hundreds or even more than 1,000 Starship launches spread over several Mars launch windows, building up a whole fleet. It sounds ridiculous at first, but there is a clear logic behind it. You are trading launch cadence and refueling complexity for speed and the payload. Instead of doing one slow, fuel-efficient transfer with a small ship, you accept a huge logistics operation, many launches, many refuels to create a few ships that can afford the Delta V for high energy, 3-month class trajectories. You are literally buying down travel time with raw propellant. But now you run into a different wall. The heating problem. Mars has an atmosphere, thin but not zero, and if you arrive going tens of thousands of miles per hour, that atmosphere becomes your main enemy. When a fast ship hits the upper layers of air, the kinetic energy gets turned into heat in a very short time. The faster you show up, the higher the peak heating on your heat shield, and the higher the total energy that shield has to absorb and survive. Protecting a large cruise ship at those speeds means bigger, heavier shields, stronger structures, more careful guidance, maybe even a combination of engine braking and atmospheric entry to keep the forces reasonable. That extra mass is not free. A heavier heat shield and stronger structure mean the ship weighs more dry even before you load propellant. A heavier ship needs more propellant to reach the same speed. That extra propellant makes the ship heavier again. You can see the loop forming every time you push toward a faster arrival. The armor you need at Mars pulls you back towards slower, safer trajectories. If you underbuild the shield and structure, you risk burning up or breaking apart. If you overbuild them, you eat into the very performance you try to gain. On top of that, mission planners have to think about G-loads on the crew. A more aggressive entry profile at high speed can mean higher deceleration forces. You might be able to survive them physically, but you do not want to design a system that slams astronauts into their seats at crushing acceleration just to save a few days. So again, you face a trade, you can go faster, but only up to the point where the heating, the structural loads, and the crew safety still sit inside acceptable limits. Then there is the last harsh truth about chemical sprints, the diminishing returns. Up to a point, adding more delta V gives you nice benefits. You go from 8.5 months to 7, from 7 to 6, maybe from 6 down towards something like 4. But once you start trying to cut below around 3 months with purely chemical propulsion, the math gets ugly. Every extra week you shave off starts to cost a lot more propellant than the week before. The rocket equation is not your friend here. To get more speed, you need more propellant, which makes the ship heavier, which means you need even more propellant to push that extra mass. You quickly reach a regime where most of your vehicle is just fuel, tanks and engines, and the actual payload, the thing you care about, the crew habitat, life support, cargo, is a small fraction of the total mass. At that point, you're basically launching a flying gas tank. You're throwing enormous industrial effort at each mission, just to pick up a small gain in speed that may not justify the risk and cost. That is the point where faster stops being worth it for chemical rockets, not because physics forbids it, but because the trade-offs become brutal in practice. So if we are already close to the reasonable limit of what chemical propulsion can do, even with giants like Starship and complex refueling operations, what do you try next if you still want to cut Mars trips even more, without turning every mission into a fuel-only monster? You want free speed to Mars, but why would you ever aim your ship at a different planet first and fly away from your target? That sounds wrong on instinct, but this is exactly what gravity assists do. And they are one of the few ways you can get a big boost in speed and without burning more propellant. You're basically telling the universe, I will take energy from the motion that's already there, instead of paying for all of it with your own fuel. So how does this actually work in simple terms you can picture in your head? Imagine your ship is falling toward a planet like Venus or Earth. That planet is already moving around the sun at a very high speed. As you fall into its gravity, you speed up relative to the planet. As you swing around and leave on the other side, the planet's gravity bends your path. If you time the approach right, you exit in a direction where, relative to the sun, your new orbit has more energy. Your speed around the sun can jump by thousands of miles per hour, and you did not have to fire your engines the whole time. You did not get magic energy. You took a tiny piece of the planet's orbital momentum. The planet slows down by an amount so small it is basically unmeasurable, and your ship gets a very real speed change. That is the core of a gravity assist. You trade geometry and timing for speed. You approach along the right path, you fly by at the right altitude and angle, you leave along a new direction, and now your heliocentric speed, your speed around the sun, is different. The only fuel you used is whatever you spent making small course corrections to hit that precise flyby corridor. Compared to a big engine burn, that cost is tiny. For a deep space mission, this is like finding an extra stage of your rocket hidden inside a planet's gravity well. So if this trick is that good, why aren't we slingshotting every Mars mission off Venus or Earth first? Why not always take the free boost? Because the universe doesn't care about your calendar, it only cares about geometry. For a gravity assist to help you, the flyby planet has to be in the right place, at the right time, moving in a direction that will bend your path the way you want. For Mars missions, that alignment does not always line up with a shorter trip time. In many cases, doing a flyby of Venus or Earth first means you add a big detour to your path. You might have to fall inward toward the sun and then come back out. Your total travel time can actually increase even though your total energy goes up. For missions that are already using low energy near Hohmann transfers, the simplest path is often just to go straight from Earth's orbit to Mars's orbit. The extra complexity and time of setting up a gravity assist is not worth it. But when you start talking about ultra-fast, high-energy missions, especially for cargo or robotic scouts, the story changes. There are trajectories where, without a gravity assist, you simply cannot get the required speed change with realistic amounts of fuel. Add a Venus or Earth flyby, and suddenly that same path becomes possible because the planet gives you a big fraction of the energy you are missing. You might ask, How big is this big shift in real numbers, not just in words? Depending on the exact geometry, a gravity assist at Venus or Earth can change your heliocentric speed by several miles per second. Remember, a single mile per second is 3,600 miles per hour, so a change of say 2 to 3 miles per second is in the range of 7,000 to more than 10,000 miles per hour of speed change. If your baseline Mars transfer was a 7-month cruise, that kind of extra energy can push your trajectory toward the 4 to 5 month range, assuming everything lines up and you are willing to accept a more complex path. The catch is that these paths can look strange. Instead of a clean curve from Earth to Mars, you might see a trajectory that first dives inward toward the Sun, swings past Venus, and then arcs back out to meet Mars's orbit. Or you might see multiple Earth flybys, where a spacecraft stays in the inner solar system for several loops, using each pass to build more energy before finally setting off for Mars. Each one of those loops takes time. You trade a higher peak speed for a longer, more twisted route, and you have to decide if the net effect on calendar time is actually worth it for your mission. Then you hit another cost that shows up any time you start flying closer to the Sun, heat and radiation. If your gravity assist plan pulls your ship inward towards Venus, or even closer, the sunlight hitting your spacecraft gets stronger. The solar flux, the power per square foot of your surfaces, goes up. Your thermal control system has to work harder to keep your electronics and propellant tanks in safe temperature ranges. Radiators, insulation and coatings all have to be designed for those higher loads. That adds complexity and mass. On top of that, the inner solar system is a harsher radiation environment in some ways. You're more exposed to solar particle events, big bursts of charged particles from the sun during flares and coronal mass ejections. If a major solar storm hits while you're near your closest point to the sun, your ship and your crew can receive a higher dose in a short time. For robots, this is an engineering problem. For humans, it is a direct health risk. So the same inward dive that helps your trajectory might also push your radiation and thermal design to the edge. This is why gravity assist trajectories are not free in the bigger sense. You save on propellant for major engine burns, but you pay in time, in navigation complexity, in thermal and radiation stress, and in the need for very accurate flyby targeting. You need precise tracking, precise course corrections, and good models of the planet's gravity field to make sure you hit the right corridor. If you miss by too much, you lose most of the benefit, or even end up in a worse orbit than you planned. Where gravity assists really become interesting for the Fast to Mars story is when you combine them with advanced propulsion instead of plain chemical burns. Imagine you already have a more powerful engine, like a nuclear thermal rocket or a high-power plasma drive. On their own, these systems can give you higher speed for the same amount of propellant, or the same speed for less propellant. Now add a gravity assist on top of that. Your engine pushes you into a high-energy path, the planet flyby tilts and boosts that path even more, and you get a combined effect that is bigger than either one alone. You can think of it this way: the engine is how hard you can push, the gravity assist is where and when you choose to apply that push. A nuclear or plasma engine gives you the power to reach more extreme flyby conditions. The flyby then multiplies your effort by letting you trade geometry for even more energy. Together, they open up trajectories that chemical rockets alone could not reach, and that pure Hohmann transfers could never touch. This is where you start to see numbers that talk about cutting Mars trips down by months, not by a few days. So you've seen what you can do by reshaping the path and stealing a little energy from planets without touching the basic engine. But what happens when you stop accepting chemical rockets as your main drive at all, and you put a nuclear reactor in the back of the ship to heat your propellant directly? How much can you shrink that 6 to 9 month window then, before you run into a completely new set of risks? You've pushed chemical rockets close to their limits, so the obvious next question is, how do you get faster without turning every Mars ship into a giant fuel tank? At some point, you stop trying to squeeze tiny gains out of chemical reactions and you change the reaction itself. Instead of burning fuel with oxygen and throwing hot exhaust out the back, you start using a nuclear reactor as your heat source. Now you are not just tweaking the transfer, you're changing the engine class. At the core, a nuclear thermal rocket is very simple to describe. You carry a tank of very light propellant, usually liquid hydrogen. You also carry a compact nuclear reactor. Instead of burning the hydrogen with oxygen, you pump that hydrogen through the reactor core. The reactor heats the hydrogen to extremely high temperatures, it expands, and you accelerate it out the nozzle. Because hydrogen is so light, and because the temperatures are so high, the exhaust leaves much faster than it does in a chemical rocket. In rocket terms, your specific impulse, basically your miles per gallon in space, is about twice as good as chemical. If a good chemical engine gives you a few hundred seconds of specific impulse, a nuclear thermal engine can be around double that. Twice the efficiency is not a small upgrade. It means that for the same amount of propellant, you can get roughly twice the total change in speed, or for the same mission, you can carry less propellant and more payload. For Mars, it means you can design transfer orbits that are shorter in time without jumping to impossible fuel loads. You're still doing a burn coast, burn style mission, but your burns now move you onto higher energy trajectories with less propellant penalty. In other words, you start to bend the chemical limits in your favour just by swapping the heat source from combustion to fission. So how much time do you actually save if you put these engines into a real Mars architecture? NASA studies and trade analyses suggest that first-generation nuclear thermal systems could bring Earth-Mars transit times down to around 120 days, about 4 months, in some mission designs. In more conservative setups, or with heavier payloads, you might see 150 to 220 days, so about 5 to 7 months. Even on the higher end, you are shaving months off the typical 6 to 9 month chemical Hohmann-style trip. On the aggressive end, you are cutting the journey almost in half. This is where the difference really shows up, not as some fantasy 3-week sprint, but as a solid, realistic step down in travel time that still fits inside what current engineering could plausibly build. You do a strong nuclear burn leaving Earth orbit, you get onto a higher energy path, you coast for less time than a chemical mission, and then you do another strong nuclear burn to slow down near Mars. The path is still an orbit around the Sun, you're not breaking physics, but the parameters of that orbit are shifted toward fast instead of cheap. A natural worry here is that you might be trading speed for weak thrust. Like ion engines that push very gently, that is not the case. Nuclear thermal rockets are high thrust systems. Concept designs and past test programs point to engines with thrust levels in the range of 50,000 to 75,000 pounds of force per engine, sometimes more in some proposals. That is not as insane as a giant booster first stage, but it is easily comparable to upper stage chemical engines. You can light the engine, accelerate hard for several minutes, then shut down. Over an entire Mars mission, the total engine on time for a nuclear thermal stage is measured in less than 2 hours, spread across a few big burns. You're not doing a continuous push for months. You still fly a burn coast burn profile just at higher energy. Short intense burns at the start and near the end, then long periods of coasting at a cruise speed higher than a chemical mission would allow for the same fuel fraction. From a mission design standpoint, this is attractive because it fits nicely with how we already fly deep space missions, just with a stronger engine. Of course, you do not get to put a nuclear reactor on a ship without thinking hard about radiation. The reactor is a source of neutrons and gamma rays when it is operating, and it will stay radioactive even when it is shut down. But there is a key advantage here. The radiation is located at the back of the ship, not inside the crew. You can separate the reactor and the crew module with a long structural truss tens of feet to hundreds of feet. You can place your liquid hydrogen tanks between the reactor and the crew habitat, so the propellant itself acts as a shield. You can also use dedicated radiation shielding around the reactor in the directions where you care most. Most of the serious risk is in launch and early operations. You do not want to lose a reactor into the ocean or the atmosphere. And you do not want an accident while you are still in low Earth orbit. That is why many designs talk about only starting the reactor once you're on a safe escape path, or after you have raised the orbit high enough that debris would not come back down quickly. Once you're in deep space and the reactor is running, the main question becomes how well you have designed your shielding and your truss length. Done right, The dose at the crew module can be kept within acceptable limits, comparable to what you would see from cosmic rays anyway. There is also history behind this. Nuclear thermal rocket concepts are not just drawings. In the 1960s and early 1970s, programs like NERVA in the United States actually built and tested NTR engines on the ground. These reactors heated hydrogen and demonstrated performance in the range we're talking about now. The engines were never flown, mostly for budget reasons, not because the physics failed. That matters for confidence. You're not starting from zero, you're picking up an old, proven physical idea with modern materials, simulation tools, and mission needs. This combination is exactly why nuclear thermal rockets are often seen as the favourite candidate for the first fast human Mars missions. They sit in a sweet spot. On one side you have chemical rockets, fully mature, but stuck with low efficiency, forcing long trip times unless you throw absurd amounts of propellant at the problem. On the other side you have very advanced ideas like fusion, antimatter, or extreme plasma drives, which are powerful on paper but far from flight-ready. Nuclear thermal sits in the middle. It uses real reactor physics we already understand, it has test data, and its performance gains are big enough to matter for humans, but not so wild that they require new physics. You can think of it less like a sci-fi warp drive and more like taking the idea of a nuclear submarine and applying it to a rocket stage. It is still a big engineering jump. You still need to solve serious safety issues, but the basic technology is close enough that major space agencies and companies are studying it for use in the coming decades. If you can routinely cut Mars trips down into the 4 to 6 month range with better safety margins and more mass at your destination, the whole picture of human Mars exploration changes. The obvious next question is, if a nuclear thermal rocket already cuts months off the trip just by heating hydrogen and doing a few short burns, what happens when you use a reactor not just to heat propellant, but to power ultra-efficient engines that run almost constantly, slowly but relentlessly building up speed toward Mars? You're used to rockets that fire hard for a few minutes, then shut off and coast. So the idea of getting to Mars faster with engines that feel weaker than a desk fan sounds totally backwards. But this is where nuclear, electric, and ion propulsion flip your intuition. Instead of one big shove, you get a slow, constant push that almost never stops, and over millions of miles, that adds up to serious speed. The key idea is simple. You use a nuclear reactor not to heat propellant directly, but to generate electricity. That power feeds ion or Hall effect thrusters at the back of the ship. These engines don't throw out hot gas in big blasts like a chemical rocket. They take a propellant, usually a heavy gas like xenon, strip electrons off the atoms to make a plasma, and then use electric fields to fling those ions out the nozzle at extremely high speed. The thrust from one thruster can be tiny, ounces to a few pounds of force, but the engine can run for months or even years. With this setup, your trip to Mars looks very different. You leave Earth orbit, you point the thrust roughly in the direction you want to go, and you keep the engines running. Day after day, week after week, you're slowly accelerating. Your path around the sun is not a clean ellipse anymore. It's a spiral that stretches outward as your speed builds. Around the halfway point in the trip, you flip the ship so the engines point forward, and you spend the rest of the journey thrusting in the opposite direction, bleeding off speed so you arrive at Mars at a safe relative velocity. The engine is almost always on, just quietly changing your orbit inch by inch, mile by mile. Why bother with such tiny thrust? Because each pound of propellant does way more work for you. In chemical rockets, even the best engines only get a few hundred seconds of specific impulse, which you can think of as efficiency, how long a unit of propellant can produce 1 unit of thrust. Ion engines can reach 3,000 seconds or more. In plain terms, you get on the order of 10 times the miles per gallon of a chemical rocket. You're throwing less mass out the back, but you are throwing it out at much higher speed, so the total energy per pound of propellant is huge. The trade is obvious. Ici symbole flippos. You get insane efficiency at the cost of low thrust and long burn times. A chemical engine dumps a lot of energy in a short burst. An ion engine stretches that energy out into a long, gentle push. For missions where you can afford that patience, the payoff is big. By the time you are halfway to Mars, your slow constant acceleration has built up a cruise speed. A chemical mission would struggle to match without massive fuel tanks. This is not just theory. We've already flown ion propulsion in deep space. NASA's Dawn mission is a good example. It used xenon-ion engines to first reach and orbit the asteroid Vesta, then leave Vesta, cruise through the asteroid belt, and enter orbit around the dwarf planet Ceres. A chemical spacecraft would have needed far more propellant to perform multiple orbit insertions like that. Dawn showed that ion thrusters can run for years, rack up huge total changes in velocity, and do complex orbital maneuvers that would be very hard with traditional propulsion. Now imagine taking the same concept, but instead of solar panels powering a few kilowatts of ion thrust, you put a nuclear reactor on board that delivers hundreds of kilowatts, or even a megawatt of electric power. Suddenly you can run many thrusters at once, or run a smaller number at higher power. Your total thrust is still small compared to a chemical rocket, but it's no longer tiny. Over months, that continuous push can give a heavy cargo ship a total change in speed that beats a standard 6 to 9 month Hohmann-style chemical transfer to Mars. This is where nuclear electric starts to beat chemical propulsion for certain jobs. If you're moving cargo, you don't care about acceleration forces in the same way you do with humans. You care about total trip time and how much mass you can deliver. A nuclear electric cargo tug could, in principle, leave Earth orbit, spiral outward under constant thrust, and make it to Mars in less time than a minimum energy chemical trajectory, while carrying more useful cargo per pound of propellant. It might not hit the 90-day mark people dream about for cruise, but cutting a cargo trip from 8 or 9 months down to say 4 to 6 months is already a big win. You can also use this system in more flexible ways. Maybe you're not trying to chase the absolute shortest calendar at a time, but you want a trajectory that's less tied to narrow launch windows, or one that arrives at Mars with more comfortable approach speeds. Continuous thrust vehicles give mission planners more knobs to turn. They can shape paths that would be very hard to fly with just 2 or 3 big burns. And because the engines sip propellant so efficiently, you can spend a lot of that performance on safety margins and flexibility instead of pure speed. But the catch is nasty, and it shows up in hardware, not in math. To get meaningful thrust from ion engines, you need a lot of electric power. That means a space nuclear power plant in the megawatt class. You need the reactor itself, shielded and mounted away from the main habitat, plus power conversion systems to turn reactor heat into electricity. Then you need radiators to dump the waste heat from those systems into space. Space is cold, but it's also a vacuum, so the only way to get rid of heat is to radiate it away. Large radiators can be the size of football fields when you deploy them, big fragile structures with strict thermal and structural requirements. All of that hardware adds a huge amount of mass and complexity. The ship grows into a long truss with a reactor on one end, radiators stretching out like wings, propellant tanks, clusters of thrusters, and finally a payload module at the front. You have to launch all of that in pieces, assemble it in space, qualify it for years of continuous operation, and prove that it can ride out micrometeoroid hits, thermal cycling, and all the other problems of deep space. From an engineering and cost point of view, this is a serious step up from even a nuclear thermal stage. That is why most realistic roadmaps put nuclear, electric, and ion drive systems in the cargo-first category. Before you ever put a crew on something like this, you will probably see uncrewed tugs hauling fuel, habitats, supplies, and equipment between Earth orbit and Mars orbit. These ships can afford longer shakedown periods. They can accept more risk, and if one fails, you lose hardware, not lives. As the technology proves itself, gets refined, and mass comes down, you can start asking the harder question: is it worth building a crew version, or do we keep using nuclear electric as the backbone of a fast cargo supply chain that supports faster, higher thrust crew vehicles? So you have seen what happens when you use a reactor to power engines that push constantly but gently. The next step up is more aggressive, a class of plasma rockets that promise both high efficiency and serious thrust at the same time. And that's where the talk shifts from months cut off to 2-month Mars runs that really start to threaten the whole 6 to 9 month paradigm. You've seen chemical rockets pushed to their limit. You've seen nuclear thermal and nuclear electric. So the next logical question is there anything that can hit Mars in about 2 months without jumping straight to pure science fiction? This is where plasma rockets start to look like the first real candidate for crazy fast but still physically possible, especially the pulsed plasma concepts NASA is starting to study. The basic idea of a pulsed plasma rocket is simple to say and brutal to execute. Instead of burning fuel in a steady flame, you take propellant, turn it into plasma, and then fire it out the back in rapid controlled pulses. Each pulse is a tiny contained blast of super hot electrically accelerated plasma. One pulse doesn't do much. But if you're firing these pulses over and over at high power, you start stacking up serious thrust while keeping the exhaust velocity extremely high. That combination gives you both force and efficiency at the same time. On paper, this is how you get to that 60-day Mars number. You leave Earth, you fire the plasma drive, and you keep it working long enough to build up speed that standard rockets just cannot touch without impossible fuel masses. You're aiming for a mission where the total trip time is on the order of 2 months instead of 6 to 9, even with a sizable crew vehicle. The timeline shrinks so much that Mars starts to look less like an expedition and more like a long deployment. To see why this is such a big deal, look at the performance numbers people talk about for these engines. A good chemical rocket tops out around 450 seconds of specific impulse. Nuclear thermal rockets might get around twice that. Some pulse plasma rocket concepts target around 5,000 seconds of specific impulse, more than 10 times chemical. That means each pound of propellant buys you an enormous amount of velocity change. At the same time, the thrust levels being discussed are not tiny. We're talking about up to 100,000 newtons of thrust, which is over 20,000 pounds of force. That's in the same neighbourhood as big upper stage engines, but with far better efficiency. High thrust and high efficiency together are exactly what faster Mars needs. High thrust gives you strong acceleration and strong braking so you can speed up and slow down in reasonable times. High efficiency means you don't need to carry a mountain of propellant to do it. With a pulsed plasma rocket, the mission profile stops looking like short burn, long coast, short burn, and starts looking more like accelerate hard for a chunk of the trip, then flip and decelerate hard for the rest. This is also why plasma rockets change how you think about the trajectory itself. With a chemical or nuclear thermal mission, you usually plan a small number of major burns and then coast in between. The orbit you take around the Sun is mostly set by that initial burn. With a powerful plasma drive, you're not locked into that. You can keep adjusting your path continuously. You can speed up, turn slightly, refine your arrival speed, tweak your closest approach to the Sun for an O-berth maneuver, and then correct again. The trajectory becomes something you actively shape from start to finish. For the crew, that matters a lot. A drive that can pull a steady fraction of a G for a while lets you design smoother acceleration profiles, keep G-forces in the comfortable range, and still reach enormous speeds. A shorter trip time means less radiation exposure, less time in microgravity, and fewer days where any random failure can grow into a mission-ending problem. You're trading one kind of technical difficulty, the engine, for a lot of safety gains in the rest of the mission. But you do not get any of this for free. The moment you look under the hood of a pulse plasma rocket, you're in full engineering hell mode. First, you need huge amounts of power. To accelerate plasma to those high exhaust speeds and produce tens of thousands of pounds of thrust, you're talking about reactor power in the megawatt to tens of megawatts range, maybe more depending on design. That means a big, high-output nuclear power system in space, plus heavy power electronics and switching systems that can handle rapid, repeated pulses without burning themselves out. Next, plasma control is not easy. You have to form, confine, and accelerate plasma pulses in a very precise way, over and over for months, without letting them damage the engine or the rest of the spacecraft. Magnetic fields have to be shaped and timed correctly. The pulse energy has to be stable enough that you don't get huge vibrations or uneven thrust. Any instability can mean erosion of critical parts, loss of performance, or outright failure. Keeping a system like that under control is not just harder than chemical, it is a different level of difficulty. Then you hit materials. Every pulse is slamming super hot, high-speed plasma through parts of your engine. Over time, that wears surfaces down, heats structures, and tests the limits of whatever alloys and ceramics you use. You can't just swap in standard rocket engine materials and be done. You need materials that can survive extreme thermal and mechanical stress, plus constant exposure to reactive plasma for months. If you underestimate this, your engine slowly destroys itself in the middle of the trip. All of that together is why this is not just the next engine, it's closer to a Manhattan Project scale technical challenge. You're combining nuclear power, high-energy plasma physics, advanced materials, and long-duration reliability, all in one package, in space with human lives depending on it. That's a much bigger jump than going from chemical to nuclear thermal, or from chemical to simple ion thrusters. Even with that, you should take it seriously because the work is already in motion. NASA and other groups are putting real money and real research time into pulsed plasma and related high-performance electric propulsion concepts. The physics is not fantasy. It's based on plasma behavior we already study in labs and on technologies we've already tested at smaller scales. The open question is not, is this allowed by physics? It is, can we build it at scale, make it reliable, and make it safe enough to put at the heart of a crewed Mars ship? If the answer to that becomes yes, even for early versions, it doesn't just shave a few days off the trip, it rewrites the whole Mars timeline. A 2-month transfer changes how much food and water you need, how much radiation shielding you need, how you design launch windows, how evacuation or rescue scenarios look, and how people psychologically think about living and working on another planet. In that world, the slow 8-month chemical mission looks more like a fallback option than the default. So if plasma rockets promise 2-month runs by throwing enormous power at the problem, is there any way to go faster or smarter without hauling that much propellant at all? Maybe by using something that's already filling space everywhere, like light itself. You keep hearing about bigger rockets and hotter engines, so it almost sounds wrong to say, try turning the engines off and just use light. But that is exactly what solar sails do. And for certain kinds of Mars missions, especially robotic ones, they could quietly change how fast the whole Mars system works, even if you never sit on one yourself. Start with the simplest version, no lasers, no reactors, just sunlight. A solar sail is a huge, thin, reflective sheet stretched out like a giant mirror. Sunlight hits it, photons bounce off, and each photon transfers a tiny bit of momentum. The push on any one spot is microscopic, less than the weight of a feather spread over a big area, but it never stops. As long as the sail faces the sun and keeps its attitude under control, it is under constant, gentle acceleration. Over millions of miles, that constant push adds up, especially if the payload attached to the sail is very light. This is not like a rocket blast, you do not feel a kick. It is more like always having a slight tailwind in space, pushing you a little harder every second. Near Earth, the acceleration might be only a tiny fraction of 1,000th of a g. But put that on a craft that weighs almost nothing, and over weeks and months you start to see real changes in speed. You're trading raw thrust for endless runtime, in the same way ion drives do, but without burning any propellant at all. The fuel is sunlight, and you do not run out of that between Earth and Mars. This idea has already been tested for real. Missions like LightSail 2 have flown solar sails in Earth orbit and shown that you can not only get thrust from sunlight, but also steer and control it. LightSail 2 used the pressure of sunlight to slowly raise its orbit, adjusting the angle of the sail on each pass. It was small, it was limited, but it proved the core point. You can sail in space the way you tack a boat in the wind, turning light pressure into useful motion with no onboard propellant. Now scale that up in your head. Take a sail much larger than LightSail, make it extremely light with advanced materials, attach a tiny Mars probe to it, and you can start designing interplanetary trajectories. The sail would not leave Earth and go straight at Mars, it would spiral outward, adjusting its orientation relative to the sun to shape its path. Given enough time and careful control, it can intersect Mars's orbit at the right point, arriving with a useful speed without ever firing a chemical engine in deep space. The calendar time might still be in the range of a few months, but you have saved enormous mass by not carrying propellant. Where this gets a lot more aggressive is when you stop relying only on sunlight and start adding lasers. Imagine building a massive laser array on Earth's surface or in Earth orbit. Instead of just letting the sun push on your sail, you focus a powerful laser beam onto it as well. Now the sail is being hit by a much more intense stream of photons, all travelling in one direction. The radiation pressure goes way up. The forces on the sail are still gentle compared to a rocket, but they are far larger than sunlight alone. With a strong enough laser, you can push a lightweight sail and payload to tens of thousands of miles per hour over a relatively short distance. You aim the laser, you power it up, and for as long as the beam stays on target, the sail keeps gaining speed. Once the craft is far enough away that the beam spreads too much or the line of sight is lost, you shut the laser off, and the sail continues on with the velocity it has built. In principle, you could accelerate a very light Mars-bound probe to speeds that beat many chemical missions, and you still have not burned propellant on the spacecraft itself. Of course, the details are ugly. You have to keep a tight beam on a moving, faraway sail. You have to manage heating, because that much laser power will warm up the sail material. You have to prevent the sail from warping or tearing under uneven forces. But if you solve those, you have a propulsion system where the heavy, complex part, the laser, stays at home, and the spacecraft is just a thin sail and a small payload riding a beam to Mars. So where do sails actually win, and where do they fall apart? For human missions, they are a hard sell. A crewed Mars ship is heavy. To get meaningful acceleration from sunlight or even lasers, you would need a sail area that is absolutely massive, with structures strong enough to handle the deployment and the forces, and control systems that can manage that huge surface precisely. The acceleration would still be very low, so trip times might not beat what you can do with powerful rockets. Also, maneuvering a huge sail with humans on board through all phases of a Mars mission adds a lot of complexity and risk. For small robotic payloads though, sails are very attractive. If you keep the payload down to a few pounds or tens of pounds, and you build a sail that weighs even less, you can get a very high acceleration compared to the total mass. That makes sails and laser pushing a perfect match for scouts, sensor platforms, communication relays, and emergency cargo. You can imagine firing off a sail-driven package ahead of a crew mission, carrying medical supplies, spare parts, or a high-bandwidth comm relay that gets into position quickly without needing a full chemical or nuclear transfer stage. That's how sails make Mars travel feel faster, even if people never ride them. A network of sail-launched probes and relays could be constantly moving between Earth and Mars, filling gaps in coverage, scouting new landing sites, measuring space weather, or delivering urgent but lightweight cargo. When a cruise ship launches, it is not alone in a big empty gap. It is flying into an environment where many small assets got there first, using light as their only push. The real long-term impact is even bigger when you think about infrastructure. If you build huge laser arrays that can push sails, those same systems can be used to send power to other spacecraft, to track and communicate with fast vehicles, and to experiment with beamed propulsion for more conventional ships. You might have a future where cargo is launched from Earth orbit on laser-pushed sails, while crews leave on nuclear thermal or plasma-powered vehicles, and both are supported by a mesh of laser and sail hardware already in space. In that setup, getting to Mars fast is no longer just about the rocket attached to the crew module. It is about the whole ecosystem, where directed energy, precision tracking, and propellant-free push all play a role. You could see laser-pushed cargo blazing the trail, nuclear stages hauling humans, and solar sails constantly moving small systems around to keep the route supplied and monitored. Time, not just fuel, becomes the main thing the whole system is designed around. So if you can use sunlight and lasers to move small payloads quick, and you can use nuclear and plasma to shove big ships faster, is there any world where you go one step further and make the engine itself run on the same process that powers stars, or even on matter and antimatter, to smash Mars trip times down from months to just a few weeks. You've seen rockets that burn entire skyscraper-sized tanks just to get a few miles per second of speed. So here's the uncomfortable question. How much faster could you go if your engine ran on the same kind of reaction that powers stars, or even on matter and antimatter themselves? At this point, you're right on the edge between serious physics and ideas that feel almost fake, but they still matter, because they tell you the absolute upper limit of how fast a Mars trip could ever get. Start with fusion, the process the sun uses. In a fusion rocket, you don't burn fuel with oxygen, you take very light nuclei, things like deuterium and tritium, which are forms of hydrogen, and you fuse them together. When they fuse, a tiny bit of their mass turns into energy. Per pound of fuel, that energy is way beyond anything you get from chemical reactions, or even normal fission reactors. The idea is to use that fusion energy to either heat a propellant or directly push charged particles out of the back of the engine. When you run the numbers, theoretical fusion rocket designs talk about specific impulses in the tens of thousands of seconds. Compare that to a few hundred seconds for chemical rockets, or maybe a couple thousand for advanced ion drives. You're talking about a system where every pound of propellant buys you a ridiculous amount of velocity change. At that point, propellant stops being the main thing holding you back. The real limits become how much thrust you can generate, how much heat you can handle, and how you keep the whole system steer. If you can get that kind of efficiency with decent thrust, the shape of a Mars mission changes completely. Instead of doing one big burn, coasting for months, then doing a second burn, you could do something much closer to continuous acceleration and deceleration. You leave Earth, point the engine one way, and accelerate at a small fraction of Earth gravity, maybe a few hundredths to a few tenths of a g. That's gentle enough for humans to live with long term, but strong enough that your speed keeps building. Midway through the trip, you flip the ship, aim the engine forward, and thrust in the opposite direction to slow down toward Mars. Under those conditions, trip times drop out of the months mode and into the weeks mode. Instead of 7 months, you start seeing trajectories in principle that take a few weeks to maybe a month, with cruise speeds climbing into the hundreds of thousands of miles per hour. The exact numbers depend on the engine design and how much acceleration you can safely sustain. But the key point is this. You are no longer talking about cutting a month or two off a chemical mission. You are talking about wiping out most of the travel time entirely. Then there's antimatter, which is even more extreme. For every normal particle, like an electron or a proton, there's an antimatter partner with the same mass and opposite charge. When matter and antimatter meet, they annihilate, and all of their mass turns into energy. No leftovers. In terms of energy per pound of fuel, antimatter annihilation is off the charts, around 10 billion times the energy density of chemical fuel. In principle, that means a few pounds of antimatter, handled correctly, could power an entire Mars mission at insane performance levels. You can imagine different ways to use that energy. You could let matter and antimatter annihilate and then use the energy to heat a propellant, similar to a nuclear thermal concept but much more powerful. Or you could use the reaction to generate huge amounts of electricity and power advanced electric or plasma engines. In the most aggressive concepts, you might even try to direct the charged particles from the annihilation itself as thrust. In all of those cases, the specific impulse you get is way beyond fusion alone, and way, way beyond chemical. On paper, that gives you the ability to design Mars trips that almost stop caring about distance. A 30-day Mars mission becomes trivial. You could push harder and design missions where the trip time is a couple of weeks. Continuous low acceleration, high peak speeds, fast braking all become possible. The vehicle could even run gravity by thrust, where the engine's acceleration gives you an artificial gravity environment for most of the trip, helping with health issues like bone loss and muscle wasting. The problem is not the physics, it's everything else. Fusion power on Earth is still struggling just to break even, meaning getting more energy out than you put in to run the reactor. The machines that do it, like big magnetic confinement devices or laser fusion setups, are huge, complex and heavy. Shrinking that down to something you can fly on a Mars ship, run safely for weeks and control precisely is far beyond what we can do today. It's not impossible in principle, but it's not a next decade engineering project either. Antimatter is even further out. We can already make antimatter in particle accelerators, but only in tiny amounts, nanograms, at absurd energy and money cost. Storing it is its own nightmare, because if antimatter touches normal matter, it annihilates instantly. You need perfect vacuum, electromagnetic traps, and fail-safe systems so that even if something goes wrong, you don't get an uncontrolled energy release, building up even milligrams, never mind pounds of antimatter, and storing them for long periods in space is far beyond our current industrial and technical capability. So yes, if you had mature fusion rockets or antimatter drives, you could make 30-day Mars trips feel routine. You could chain missions together in rapid cycles, send rescue vehicles that catch up in days, and treat the Earth-Mars distance almost like a long-haul airline route instead of a deep space expedition. But no, these are not your near-term solutions. We're still at the stage where Earth-based fusion power plants are experimental, and antimatter is an expensive lab curiosity. They still matter to the story for a different reason. They set the horizon. They mark the far edge of what fast to Mars could mean if you push technology for decades or centuries. Every realistic system you've heard so far, chemical sprints, nuclear thermal, nuclear electric, plasma drives, gets compared against this frontier. How close does it get to the ideal fusion or antimatter mission profile? If a new concept can move you even partway towards those weeks, not months trajectories, it's a big deal. And there's one more hard lesson that fusion and antimatter make painfully clear. Even if you had an engine powerful enough to hit hundreds of thousands of miles per hour, you still have the same final problem. You must somehow slow down near Mars without tearing the ship apart or wasting all your hard-earned speed. So the next question is simple and brutal. Once you've gone fast, how do you hit the brakes without paying for it with the same huge amount of fuel you just saved? Getting to Mars fast is pointless if you arrive so fast you can't survive the stop. You're not parking a car here. You're showing up at a planet going maybe 50,000 miles per hour or more, and you have to lose almost all of that speed without ripping the ship apart or boiling your heat shield. That arrival problem is half of every fast mission design, and honestly, it's the part that keeps mission planners awake at night. So picture this in simple terms. You've done the hard work, you've burned like crazy leaving Earth, maybe used nuclear, maybe high-energy chemical, maybe even some wild advanced engine, and now Mars is rushing up at you. At that point, you have two options. Either you use engines again to burn a ton of propellant and slow down the normal way, or you dive into the atmosphere and let Mars itself do the braking for you. If you don't do either hard enough, you skip past Mars and lose the mission. If you do it wrong, you hit the air so fast your heat shield turns into a glowing cloud and takes the ship with it. That's where aerobraking and aerocapture come in, and they're both just different ways of saying, use the atmosphere as a brake instead of your engines. Aerobraking is the gentle version. You already arrive in orbit, but your orbit is big and high energy. On each pass around Mars, you dip the spacecraft into the thin upper atmosphere for a short time, just enough to scrub off a little speed through drag. Then you come back out, complete the orbit, and repeat. Over dozens or even hundreds of passes, your orbit shrinks and your speed drops. You pay in time, but you save a massive amount of propellant. Aerocapture is the aggressive high-stakes move. You don't show up already in orbit. You arrive on a fast incoming trajectory, you aim for a very specific altitude and angle, and you do one deep pass through the atmosphere. In that single pass, you dump a huge chunk of your speed into heating the air in your heat shield. If you nail it, you exit that pass already captured into a bound orbit around Mars, with way less need for engine burns. If you come in too deep, you overheat and possibly burn up. Too shallow, and you skip out and leave Mars behind. Fast missions lean hard toward aerocapture, because when your cruise speed is high, engine braking at arrival gets expensive very fast. You'd need a huge amount of propellant just to cancel out the velocity you built up. If you can instead design a heat shield and guidance system that can take that monster first atmospheric pass, you've basically bought a massive velocity change for free, in terms of fuel. The real cost is in designing and testing a vehicle that can ride that kind of entry without coming apart. Now, even before you get to Mars, there's another trick you can use both at departure and arrival that lets you squeeze more performance out of the same propellant, and it sounds almost too simple: burn where you're going fastest. When you're in orbit around a planet, there's a point in that orbit where you're closest to the planet. That point is where your speed is highest. If you fire your engines right at that closest point, each bit of propellant you burn adds more energy to your overall orbit than it would if you burned somewhere else. That's called the Oberth effect. Think about it like this: your engine doesn't know whether you're going slow or fast. It just adds a certain amount of speed relative to where you already are. If you're already flying very fast near a planet and you add a little more, the energy gain you get in your orbit around the Sun jumps by a lot. So a burn of, say, 1 mile per second near your closest point to Earth can raise your solar orbit energy way more than that same 1 mile per second burn done far out in deep space. Yeah, where you're moving slower. For Mars missions, that means 2 big opportunities. First, you can leave Earth in a smart way. Instead of just doing one big burn from low Earth orbit and heading out, you can dip a little deeper into Earth's gravity well, or time your burn perfectly at the lowest point of your parking orbit, and use that Oberth boost to sling yourself onto a higher energy trajectory for the same fuel. Second, on arrival, you can combine this with Mars itself. Either you do a powered burn at your lowest point near Mars, on top of an atmospheric pass, or you design a trajectory where a small engine burn at the right moment replaces a much larger burn you would have needed otherwise. Mission studies that combine all this, high-efficiency engines like nuclear thermal or advanced electric plus Oberth maneuvers, plus aerocapture, show that you can push transit times down into that 3-month range without asking for totally insane delta V numbers. The math behind those trajectories is messy. You're optimizing where to burn, how deep to go into the atmosphere, how much you trust your heat shield and structure, and how much risk you're willing to eat. But the underlying physics is solid. Burn when you're fast, let atmospheres do some of the braking, and you get more trip for every pound of propellant. Here's the part that feels backwards at first. Good braking is actually what enables you to go faster in the first place. If you know you can slow down cheaply at Mars using aerocapture, and you know you can get extra punch from the Oberth effect both leaving and arriving, you can afford to pick more aggressive outbound trajectories. You don't have to hold back as much to make sure you can pay the arrival bill with your engines alone. Aerocapture and Oberth are like coupons for your speed budget. They stretch the value of the propellant you do bring. That changes the design mindset. Instead of tilting the whole mission toward low-fuel, long-time, safe arrival, you can tilt it toward higher energy, shorter time, still survivable arrival because your braking tools are better. More efficient braking also multiplies the value of every engine upgrade you make. If you pair nuclear thermal or powerful plasma drives with smart Oberth burns and aerocapture, you get more out of them than if you just used them like big chemical engines and coasted the rest of the way. So now there's a new tension on the table. Not just how fast can the ship go, but how much punishment can your crew and hardware take during that final slam into Mars's gravity and atmosphere. You can push the physics pretty far, but the human body and the spacecraft structure still have limits, and that's where the next layer of the problem shows up. You keep hearing numbers like 90 days and 210 days, like they're just schedule options, but your body does not see it that way at all. For your muscles, your bones, your brain, and your DNA, the difference between a 3-month trip and a 9-month trip is the difference between tough but manageable and slow grinding damage. The ship might handle a brutal trajectory. The question is whether you can. Start with the most obvious piece, acceleration. When a rocket pushes you, you feel G-forces, extra weight pressing you into your seat. 1 G is what you feel standing on Earth. Double that and you feel twice as heavy, and so on. For launch and landing, short spikes of a few G are fine. Humans have handled that many times. The real question for fast Mars missions is sustained acceleration. What happens if the engine is on for hours, days, or even weeks? The good news is that steady accelerations in the range of a fraction of a G, something like 0.1 to 0.3 G, are actually pretty comfortable for healthy people, especially if the ship is designed so your spine is lined up in a way that distributes the load through your body instead of straight through your head and feet. At 0.1 g, you feel a little heavier than weightless, but it's not crushing. At 0.3 g, you feel like you weigh about 30% more than on Earth, which is noticeable, but it's not extreme. You could live with that for weeks if the rest of this environment is controlled. The bad news is that you cannot just crank that number up and leave it there. Sustained accelerations close to 1 g or higher for long periods would beat up your cardiovascular system, stress your spine and hammer your joints. Your heart has to work harder to pump blood, your support muscles have to work non-stop against the extra weight, and any sudden maneuvers on top of that load become dangerous. Fast missions have to walk a very tight line, strong enough acceleration to get the trip done quickly, low enough that your body does not slowly fail under the constant extra load. Now layer radiation on top of that. Once you leave Earth's magnetic field, you're exposed to cosmic rays from outside the solar system and charged particles from the sun. They punch through your body and your ship, damaging cells, increasing cancer risk, and in large bursts they can cause acute radiation sickness. You can add shielding, you can pick orbits that avoid the worst parts of the Van Allen belts, you can ride out storms in a protected storm shelter section of the ship, but you cannot turn space radiation off. This is where speed quietly becomes a safety feature. Every month you're in transit is another month soaking in that radiation bath. Studies looking at high-energy trajectories for vehicles like Starship in the 90 to 104-day range are not just about shaving time for fun, they're about keeping total radiation dose within NASA's career limits for astronauts over their lifetime. Stretch those same missions out to 7 or 9 months each way, and the cumulative dose starts climbing into much more worrying territory, especially if you stack multiple missions across a career. So when you push for 3-month trips instead of 7-month trips, you are literally buying down cancer risk with engine performance. You're reducing how many solar storms you have to get lucky on. You're cutting down how long your crew has to go before they can get back under a real magnetic shield, either Mars's limited 1+ dirt and rock, or Earth's much stronger environment. Then there is the part people tend to forget until they see ISS data, what microgravity does to your bones and muscles. In 0 g, your body decides it does not need to work as hard. Your leg muscles, your back muscles, and your core start to weaken. Your bones lose density because the body is not loading them the way it does under gravity. Astronauts fight this with hours of exercise every day, resistance machines, treadmills with harnesses, and careful diet, but even with that, a long stay in microgravity leaves you weaker when you come home. Now imagine coming out of that state not onto a couch, but onto the surface of Mars. The gravity there is about 38% of Earth's. It's less, but it's still a pull your body has to handle. A 3-month trip is still rough, but it means less time for bone density to drop, less time for muscles to atrophy, and a shorter rehab period before you can safely do hard surface work. A 9-month trip means almost a full year of your body slowly downgrading before you even land, then asking it to handle landing forces, suit operations, and field work with reduced reserves. Distance in miles matters to the ship, distance in months matters to your skeleton. On top of that, you have the mental side. Nobody has spent 9 continuous months in deep space outsea Earth's magnetic field, in a vehicle small enough to be practical for Mars. We know from submarines, polar stations, and the International Space Station that confinement, isolation, and long-duration missions strain mental health. People get irritable, depressed, anxious, group dynamics shift. Minor conflicts can grow if there is nowhere to go and no break in the routine. A Mars transfer vehicle is basically a high-tech tin can with life support. The longer the crew is in there, the more chances there are for sleep problems, mood swings, interpersonal conflicts, and stress from distant emergencies. When you add in the communication delay, with signals to and from Earth taking minutes to cross the gap, crews cannot just call home and talk through every issue in real time. A faster trip means fewer days inside that pressure cooker. It means less time for small problems to snowball. It means fewer cycles of bad news from Earth, no way to help, just sit and think about it. While you are months from anywhere. So when you compare a 90-day sprint profile to a 210-day cruise, do not treat them like 2 points on a travel brochure. The shorter trip means a lower radiation dose, less microgravity damage, less psychological strain, and fewer hours where any random hardware failure can grow into a life-threatening problem. Each extra month in transit is not just more time, it's more exposure, more wear and tear, more roll of the dice. That's the real biological argument for speed. Your body, your mind, and your long-term health are quietly screaming for faster propulsion. Every improvement that cuts transit time, even by a few weeks, nudges risk in your favour. That's why so many exotic propulsion studies are not just about going fast because it's cool, they're about getting humans through the trip with less damage. The ugly twist is that as you start stacking all these tricks, higher thrust, smarter trajectories, aerocapture, tighter margins, the room for human error shrinks. You're flying closer to the edge. So the next piece of the puzzle is not just better engines, it's better brains flying the mission. And that's where advanced software and AI start quietly turning into speed multipliers too. You've now stacked up a whole menu of engines and tricks, so the next question is, are we actually flying them in the smartest way, or are we just guessing good enough routes and leaving free speed on the table? A lot of fast to Mars is not just about better hardware, it's about squeezing more out of gravity, timing and tiny burns, and that is where software, and especially AI, starts acting like invisible propulsion. Classical mission design looks impressive from the outside. You have teams of experts, big optimization codes, decades of experience. They pick a launch window, they shape a transfer, they add maybe one gravity assist, they check the delta V, and they lock it in. But even with good tools, humans only explore a small slice of what's possible. You're limited by time, by intuition, and by how many different patterns people can realistically test. The real space of trajectories is huge, with weird combinations of burns, flybys, and timing that no one would draw on a whiteboard. Once you let algorithms roam through that space, the game changes. Instead of a human saying, try this family of transfers, you set up rules and goals, and you let the code search. It can vary departure dates, arrival dates, burn magnitudes, burn directions, gravity assists, periapsis altitudes, and more, all at once. It can evaluate millions of options, not just dozens. A lot of those options will be garbage, but a few will be strange, efficient paths that save a few % of fuel, or cut a couple of weeks off the trip, or reduce arrival speed enough that your heat shield design gets simpler. That doesn't sound dramatic at first, a few weeks faster, a bit less propellant, just from better math. But remember everything you've heard so far. A few weeks less radiation, a few weeks less microgravity, a lower arrival speed that makes aerocapture safer, or a slightly wider launch window you can work with. All of that matters. And you got it without building a new reactor, without inventing new materials, just by flying smarter through the gravity you already have. Modern optimization and AI methods push this even further. You can set up multi-objective searches where the software tries to minimize trip time, fuel use, peak heating, and G-forces all at once. You can ask it to find routes that hit specific scientific or staging targets along the way, like a flyby of an asteroid or a refuel in Mars orbit. You can include uncertainties, like how much you trust your engine performance, and let the algorithm favor trajectories with more margin. The result is not one perfect path, but a set of clever options, some faster, some safer, some cheaper that humans can pick from, and that's just the planning side. Once the ship is on its way, there's a second layer, how you adjust mid-course. In a classic mission, you plan a few scheduled correction burns, you measure your actual path, you make small fixes, and you hope nothing big changes. With more autonomy and onboard AI, the ship can do a lot more. It can constantly monitor its actual trajectory against the target, look for tiny deviations, and fix them early with very small pushes instead of waiting until errors grow. It can adjust the timing and depth of gravity assists in real time to squeeze extra speed or extra safety out of them. You can also react better to space weather. If the ship sees a big solar storm coming, an onboard system could decide to shift the timing of a burn, change the orientation of the vehicle to use mass as shielding, or even make a small trajectory tweak that moves you into a slightly different part of space at the peak of the event. Those moves are measured in minutes, miles, and fractions of a degree, but they can cut radiation dose or avoid extra course corrections later. Every correction you don't have to make late in the mission is speed and fuel you keep. Now think about pairing that with the exotic engines you heard about earlier. A big chemical rocket has only a few knobs: ignition time, burn duration, thrust level, if it's throttleable. A nuclear electric tug, a plasma rocket, or a future fusion system has many more. You can vary power level, pulse rate, thrust direction, propellant flow, and more, all along the trajectory. The best way to fly those ships is not obvious. The difference between a good control schedule and a great one can be weeks of trip time and huge swings in fuel margin. At that complexity level, AI stops being nice to have and starts becoming, you can't fly this without it. An advanced engine might deliver the right performance only if it's controlled in a very specific pattern. Thousands or millions of tiny decisions over the course of the flight. Human operators on the ground, with minutes of communication delay each way, cannot micromanage that in real time. You need software that can learn, adapt, and squeeze performance out of the system safely as conditions change. There's another subtle effect here too. The more capable your software is, the more aggressive you can be in mission design. If you trust the onboard systems to handle tight gravity assists, sharp aerocapture corridors, or finely tuned burns at periapsis, you can sign off on faster trajectories with smaller margins. If you don't trust the software, you have to widen every safety zone and pad every parameter, which usually means slower, more conservative paths. Smarter navigation is not just about convenience, it directly translates into what kind of speed envelope you're willing to fly humans in. The hidden message in all of this is simple. Faster isn't just about the engine. You could launch 2 Mars missions with the exact same hardware, the same rocket, the same propellant, the same heat shield, and if one flies a hand-designed trajectory and the other flies an AI-optimized one, the AI ship might show up weeks earlier, with more fuel left and lower peak heating at arrival. The only difference is the quality of the planning and the onboard decision-making. Over the next decade or so, it's very likely you'll see Mars trajectories quietly get sharper just from better software, even before the big new engines fully mature. People will compare missions and notice that later ones are faster, not because the rocket suddenly upgraded, but because the math did. Gravity didn't change, the sun didn't change, our ability to surf those same fields more precisely did. But even perfect software and clever algorithms can't change one basic fact: small ships and rare launches will always limit how bold you can be. If you really want to treat Mars like a place you visit all the time, not once in a generation, you need more than one ship and you need more than one launch. You need a whole fleet, and you need vehicles big enough that high-energy, fast trips become normal, not special events. You want fast trips to Mars, but how far can you really go with single ships launched now and then like one-off expeditions? If you want to make fast normal, not a rare stunt, you don't just need better engines, you need bigger vehicles and a lot more of them. Speed stops being a one-ship trick and turns into a property of an entire fleet. So where does Starship really fit into this picture? Not as hype, but as a baseline Mars bus. Starship is designed to lift over 100 tons to low Earth orbit, using fully reusable stages. On its own, one fully fueled Starship leaving the pad is powerful, but the real move is what happens after it reaches orbit. You don't treat that orbital Starship as a final vehicle, you treat it as an empty tank you're about to fill. You send up multiple tanker Starships, each one meeting it in orbit, and pumping over liquid methane and liquid oxygen. After enough tanker flights, that one Mars-bound Starship in orbit ends up with its tanks topped off, far fuller than if it had to carry all that propellant off the ground in one go. With that much propellant on board in space, the delta V available, the total change in speed it can generate jumps. Now it's not just a transport for slow, energy-efficient Hohmann transfers, it becomes a high-energy Mars ship with enough punch to chase 3 to 3.5-month trajectories instead of 7-month ones, if you're willing to accept the heating and arrival challenges. Same basic hardware, but used at fleet scale, with refueling turns into something very different from a one-and-done launch. Then you hit the next question. How many of these ships are we really talking about? Elon Musk has talked openly about launching on the order of 1,000 to 2,000 Starships every 2 years, clustered around each favourable Earth-Mars alignment. That sounds crazy until you zoom out and see it as a transport system, not individual missions. In that model, a launch window isn't one or two rockets, it's a mass event, a wave of departures. In that wave, not every ship has to fly the same profile. Some vehicles can take slower, cheaper, more fuel-efficient orbits, carrying bulk cargo, construction gear, or low-priority supplies. Others can burn harder, use more refueling and take faster, more aggressive trajectories, carrying crews, critical equipment, or high-value payloads. Speed becomes a knob you turn per ship, not a rigid property of the entire program. You can choose which trips are slow and cheap, and which are fast and expensive inside the same fleet. Once you think that way, Starship stops being the end state and starts looking like the first module in something bigger. So what does beyond Starship look like if you care specifically about going fast? Think modular megaships. Instead of one integrated vehicle doing every job, you break the system into stages you can swap. You might have a nuclear thermal transfer stage that lives in orbit and never lands, built heavy and optimized only for high-energy burns between planets. Attached to that, you dock a separate chemical landing and ascent stage for Mars, built to handle atmosphere and dust and surface operations. In that kind of architecture, your Mars transfer hardware doesn't have to waste mass on landing legs, entry tiles, or ascent engines. It is pure speed hardware, used over and over across many missions. You assemble it in orbit, you refuel it in orbit, and you mate it with whatever crew capsule or cargo pod you need for that particular trip. The bigger your infrastructure gets, the more freedom you have to dedicate some pieces entirely to go fast and let other pieces focus on get down and up safely. Now ask what happens when you don't just have one megaship but many moving between Earth and Mars at the same time. This is where fleet effects start showing up, and they matter a lot for safety. If you have only one vehicle on the route, any serious failure mid-mission is an all-or-nothing crisis. If you have a dozen or more in transit on staggered paths, a faster vehicle can, in principle, serve as an emergency responder. It could adjust its trajectory, burn a little more propellant, and intercept another ship to deliver spare parts, medical supplies, or even take on some of its crew. Even if full-on rescue dockings are rare or only possible in limited cases, the presence of other vehicles on similar routes changes the risk picture. You can have redundancy in communications, you can test hardware on cargo ships before putting it on cruise ships, you can intentionally fly one very fast high-risk profile as a pathfinder, and keep the others slightly more conservative. In that environment, speed is not just a stunt, it's another layer in your safety net. You also get a different kind of learning curve. With 1 or 2 Mars missions per decade, every trajectory is precious and conservative. With dozens or hundreds of ships flying every window, iteration B comes normal. You can run A/B tests on trajectories. You can try slightly higher energy profiles, more aggressive aerocapture entries, or tighter O-berth maneuvers on selected flights, collect data, and roll those lessons into the next window. The average flight time for the fleet can drop over time, just from accumulated experience and better models, even if the engine tech doesn't change dramatically from one window to the next. Over a few cycles, that pattern adds up. Early windows might see crewed flights taking 6 to 7 months, and only a few high-priority ships running 3 to 4 month profiles. Later windows might push most crew missions toward that 3 to 4 month band routinely, with a smaller subset experimenting closer to the 90 to 100 day regime. The more vehicles you fly, the more confident you become about the actual performance envelope, not just the theoretical one. Fast stops being the exception you do once to prove a point. It becomes the new normal, because the system has had enough shots on goal to support it. At that stage, Earth-Mars travel looks less like a heroic one-off and more like a rough industrial transport network. You have big ships, refueling infrastructure, orbital depots, maybe nuclear stages, maybe advanced drives layered in over time. You can choose which knobs to turn per mission, but the overall trend is simple. Time in transit keeps getting pushed down, because the entire system is now built around making that happen. But even with megaships and fleets, you're still doing the hardest thing the hard way, lifting all that mass from sea level into orbit with classic launches. So the next obvious challenge is this. If you want truly fast Mars missions, why are you still paying full price just to reach orbit, instead of using infrastructure to fling your mass into space before the rocket even lights? You keep staring at giant rockets and exotic engines, but the biggest speed hack to Mars might start way earlier, at the very first step getting mass off Earth. Right now, every pound of cargo, every pound of fuel, every piece of shielding has to ride a chemical rocket all the way from sea level to orbit. That first climb is brutally expensive in energy. If you can cheat on that part even a little, you free up a lot of room to go faster later. So think about the simplest launch assist idea: mass drivers and railguns. Instead of putting every pound of cargo on top of a rocket, you put some of it in tough, unmanned pods, and you fire those pods up a long electromagnetic track built on a mountain slope. The track is basically a railgun or coil gun, a series of electromagnets that kick the pod faster and faster as it climbs. At the end, the pod leaves the track at several miles per second, pointed on a trajectory that reaches orbit or at least a very high altitude where a small rocket kit can circularize it. You don't put people in that, the acceleration can be huge, way beyond what a human body can tolerate. But fuel, water, metal, bulk cargo, those don't care. The pods either reach orbit directly or get close enough that a small space tug or a captured stage can grab them and finish the job. The important thing is this: your main Mars ship does not have to lift all that mass from sea level with its own engines. It meets that mass already in orbit. Every ton of propellant or cargo that reaches space this way is a ton your launch stack doesn't have to throw straight up through the thickest part of the atmosphere. Next, rotate the idea from straight rails to something that sounds insane, but sits right inside orbital mechanics: skyhooks. Picture a long tether in low Earth orbit, rotating end over end. The center of mass of the tether follows a normal orbit. The tips, though, move faster or slower relative to the surface depending on their rotation. Time things right and the lower tip of that rotating tether sweeps through the upper atmosphere with a horizontal speed that is closer to the ground's rotation speed than the orbital speed. If a suborbital vehicle launches from Earth and meets that lower tip at just the right moment, the tip can grab the vehicle with a capture mechanism. From there, the tether's rotation lifts the vehicle up and flings it to a higher orbit, sharing some of its orbital momentum. The skyhook then slows a little, and over time you reboost it with small engines or additional payload swaps. The key benefit, again, is that your Mars transfer stage starts from a higher energy orbit, having gotten some of its speed for free from the tether instead of from burning more propellant. You don't need a full space elevator to see these gains. A partial system, tens to hundreds of miles long, can still do meaningful work, especially if you combine it with high-performance upper stages. And unlike a true space elevator, a skyhook can be redeployed, adjusted, or even moved to different orbital inclinations if the architecture demands it. Then there's the idea of partial space elevators and off-world elevators. Building a full Earth to geostationary cable with current materials is out of reach. The strength requirements are brutal, but you don't have to go all the way to get benefits. Even a shorter tether, starting from a high orbit down toward the atmosphere, can reduce the delta V your launchers need to supply. You get to grab payloads that come up on suborbital hops, then pull them higher for less energy than a pure rocket solution. On the Moon or on smaller bodies, things get more forgiving. The gravity is lower, the orbital speeds are smaller, and the strength requirements for a tether drop. A lunar elevator or lunar skyhook could move propellant mined from lunar ice, metals and other resources into cislunar space with much lower rocket costs. Once you have propellant depots out there, your Mars vehicles no longer need to carry all their fuel from Earth's surface. They can top off from lunar-sourced propellant and then run higher energy, faster transfers to Mars without blowing through the launch budget. All of this points at the same basic rule for fast trips. Every pound you don't have to throw straight off Earth with chemical rockets can be reassigned. You can use that saved launch capacity to carry more fuel for higher departure speeds, heavier engines with better performance, or more shielding to make deep space radiation exposure less deadly. Launch assist systems, railguns, mass drivers, skyhooks, partial elevators are speed by subtraction. They remove the most expensive part of the climb, so you can spend more of your energy budget on the part of the trip that actually crosses interplanetary space. It also changes how you think about mission risk. A Mars mission that depends entirely on one giant rocket leaving Earth with everything on board has very little flexibility. A Mars mission that taps into a network of ground-based mass drivers, orbital tethers, and depots can mix and match. Some cargo goes up the cheap high-acceleration route. Some goes on reusable launchers. Your crew rides a safer, controlled booster, then meets their fully fueled transfer stage that was assembled and topped off piece by piece using all that infrastructure. And remember, this isn't just an Earth-side game. If you build similar infrastructure on Mars or in Mars orbit, the return trip changes just as much. Mass drivers on Martian slopes could fling bulk cargo or propellant to orbit. Tethers around Mars could catch ascent vehicles and sling them onto Earth-bound trajectories with less onboard propellant. That means coming home faster and with more margin, not just getting there fast and then crawling back on a slow, energy-saving route. The full Fast Mars picture is not a single magic ship. It's a two-planet system with both Earth and Mars equipped with hardware that cuts the cost of each link in the chain. Rapid outbound, rapid return supported by launch assist and orbital infrastructure on both sides. The better that network gets, the more reasonable 3-month, even 2-month missions start to look. Not as one-off stunts, but as part of a regular transport cycle. At that point, there's really only one question left. If you keep stacking all these upgrades, better engines, smarter routes, atmospheric braking, AI piloting, fleets and infrastructure, just how far can you push it? What does it actually take to turn a 7 to 9 month slog into a 30 to 40 day dash? And what kind of ship would have to exist for that to stop being science fiction and start being a serious concept on someone's whiteboard? You've heard 3-month and 4-month Mars trips and they already sound extreme. So now stretch your brain one more step. Imagine crossing the average Earth-Mars distance in just over 5 weeks. Concepts like the Titan Cosmos study take that seriously, not as a movie pitch, but as a physics exercise. To cover roughly 140 million miles in about 39 days, your ship has to average on the order of 150,000 miles per hour. That's not a peak, that's the average, over the whole trip. For comparison, a mission like Perseverance cruised around 24,600 miles per hour relative to the Sun. You're talking about a vehicle that spends the journey flying 5 or 6 times faster than our best Mars hardware has ever done, while carrying humans, life support and enough structure to keep everyone alive. At those speeds, the whole profile of the mission flips. You're no longer doing a big burn, a long coast and a final burn. You're running a high-performance engine for a large chunk of the trip, probably a fusion class or very advanced plasma system, and you're managing acceleration and deceleration as continuous phases. The engine isn't just something you fire at the start and end, it's the main tool you live with every day, constantly trading propellant for hours shaved off the clock. The ship isn't a passive capsule, it's an active machine that never really cruises in the old sense. The thing is, you don't even have to jump all the way to that 39-day, 150,000 mile per hour regime to see a complete change in how Mars missions feel. That pulsed plasma rocket idea we talked about, the one NASA is funding studies on, is already aiming at roughly 60-day trips with realistic, if ambitious, engineering. 2 months out, 2 months back with some stay time in between, and suddenly your mission arc starts looking less like a one-off deep space odyssey and more like an extended lunar campaign. You can imagine rotating crews, overlapping missions, resupply flights that make sense on human timescales. If you can reliably do 60-day transfers, everything in the chain gets easier to schedule. You can send cargo and crew on similar timelines instead of having hardware waiting in orbit for half a year. You can run more cycles per decade, which means more practice, more data, and more chances to refine how aggressive you're willing to be. A 60-day Mars transfer isn't just twice as fast as some of the Starship-class chemical trajectories on a paper. It shifts the mission from life event to tour of duty, still intense, Still risky, but not a year and a half of your life just in transit. So what does it actually feel like on board a ship chasing those kinds of times? Not from the outside, but in your body, day after day. To hit and manage those speeds without crushing the crew, you'd likely run at a continuous fraction of a g, something like 0.2 to 0.3 grams for stretches of days or weeks. That means you feel lighter than on Earth, but not weightless. At 0.2 grams, you'd feel like you weigh 1/5 of your Earth weight. At 0.3 grams, you'd feel like you weigh 1/3 of your Earth weight, about a third. Walking is different, lifting objects is different, but your body still has a clear sense of down, your blood still has a preferred directions, your bones and muscles still see regular load. That's a very different experience from floating in 0G for months. You'd probably align the thrust so that down is in the direction of the engine, so acceleration mimics gravity. When the ship flips at mid-course and starts decelerating, your down reverses as the thrust direction changes, which is weird but manageable if the maneuver is planned and controlled. The cabin feels like a slow elevator that never stops, but because the acceleration is gentle and steady, your body can adapt. The psychological effect of having a constant sense of weight, even a reduced one, is huge compared to drifting for months. Now the hard edge, all that speed has to go somewhere when you get to Mars. Showing up at 150,000 miles per hour relative to the planet is not something you can casually fix with a small engine burn. If you try to let the atmosphere do most of the work with aerocapture, you're asking your heat shield and structure to survive entry energies far above anything we've ever tested at that scale. Peak heating skyrockets, thermal loads on the leading edges, and shield materials push toward their limits, and small errors in angle or density can swing you between safe capture and catastrophic breakup. You can blunt that by burning a lot to slow down before you hit the atmosphere, but that means your engine has to deliver serious deceleration near arrival, which eats into your propellant margin and cuts into the performance that got you there fast in the first place. That pushes you toward very heavy, very smart shielding, both for heat and for radiation. The faster you go, the more aggressive your radiation shielding needs to be over the whole trip, because your target cruise speeds are higher and your exposure to high-energy particles can spike in odd ways when you're zipping through the solar wind and occasional solar storms. Pulling all that together means arrival is not a simple entry-descent-landing script. It's likely a finely tuned stack of powered braking, exactly timed aerocapture, and carefully chosen G-load limits. Your margins are razor thin. There's not much room for sloppy navigation or slow response. The payoff is a crew that left Earth just over a month ago and is already stepping onto Martian soil. The cost is an engineering and operations envelope where everything has to go right. Because your energy budget is so high, there's not a lot of gentle failure modes left. This is why even the jump from 7 to 9 months down to 2 to 3 months is already a revolution. At 2 to 3 months, radiation dose drops sharply. Bone and muscle loss are still a problem, but much less severe. Psychological strain is shorter, and hardware doesn't have to survive as many months of continuous operation in deep space. You can realistically plan more missions, send more people, and treat Mars expeditions as something nations or companies do regularly, not once per generation. Push that down toward 30 to 40 days and the whole relationship between Earth and Mars changes. Launch windows become less critical, because a very fast ship can handle a wider range of alignments without losing its advantage. Emergency rescues, which are basically impossible on a 7 to 9 month profile, start to at least be thinkable. A fast ship could leave on a later window and still catch up while the original crew is en route or on the surface. Supply chains tighten up with urgent cargo able to follow crews in a reasonable time frame instead of arriving half a year later. Most of all, the way people think about Mars shifts. Right now it feels like another world in the emotional sense, something distant and slow and almost unreachable for normal life. In a 30 to 40 day regime, it starts feeling closer to another continent, hard to reach, but familiar enough that you could imagine going there, working a rotation, and coming back without vanishing from Earth for years. When that psychological barrier breaks, everything else gets easier to sell: funding, training, risk, and long-term planning. So when you hear people fight for faster propulsion, it's not just because they like big numbers on a slide dim law. They're trying to drag Mars out of the once-in-a-lifetime expedition zone and into the "this is part of how our civilization works" zone, and the only way to get there is to keep attacking that transit time from every angle: engines, trajectories, infrastructure, and human factors, until months start collapsing into weeks. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.